This is yogurt. And this is yogurt too. What turned the soft yogurt into this semi-solid ball? The answer is a technique in molecular gastronomy called reverse spherification. Reverse spherification uses food-friendly chemicals to turn soft foods and liquids into spheres with a liquid center and a gelatinous outside. In this video, we'll show you how to do reverse spherification, explain the science behind it, compare reverse spherification and direct spherification, give you tips and tricks for getting the best results, and tell you how you can turn this fun cooking technique into a science project for school. Reverse spherification can be used with nearly any type of liquid or soft food. However, it works best for foods with high calcium content, such as some fruit juices or dairy products like milk, cream, and yogurt. An ideal food calcium content is around 0.2%. This is equivalent to 200 mg of calcium per 100 grams of food. You can consult the nutrition label of the food to find out about its calcium content. Usually, any food where the nutrition label shows 20% or more daily value of calcium works well. For foods with low calcium, you will need to increase the calcium content of the food by adding a calcium salt like calcium lactate gluconate. Or you can switch to the direct spherification process, which is another molecular gastronomy technique based on the same science principles. You can learn more about that in our direct spherification video as well as later in this video. Once you have chosen a food for reverse spherification, you'll need to gather these materials. Follow the link in the description for a detailed list. First, make the sodium alginate solution, which will be your setting bath. Weigh out 2.9 grams of sodium alginate and measure out 3 cups of distilled water. It is important to use distilled water as it is calcium-free, unlike a lot of tap water and bottled water, which often have small amounts of calcium. Mix the sodium alginate with the distilled water in a blender by adding a little bit of the alginate and water at a time. If your blender is small, you can make several batches. Make sure the solution is well mixed. Cover the mixed solution and place it in the refrigerator overnight to remove the air bubbles created in the blender. Once the sodium alginate solution is bubble-free, prepare your chosen liquid or soft food. It is best to start with food that has been chilled for several hours. If your food does not contain enough calcium, you will need to add calcium lactate gluconate. Only 10% of the calcium lactate gluconate salt is actual calcium, so you will need to add about 2% of your chosen liquid's weight in calcium lactate gluconate to your liquid food to obtain a food solution with 0.2% calcium. For 100 grams of food, this would be 2 grams of calcium lactate gluconate. Whisk the food calcium mixture until the calcium salt is completely dissolved. Since yogurt is calcium rich, you won't need to add any calcium salt for making yogurt spheres. To make the best spheres, your food mixture should have the consistency of thick cream. If your food is too thick, you can dilute it with milk or water. If it is too thin, you can add xanthan gum to your food to make it thicker. Put a drop of vegetable oil on a paper towel and grease the inside of a tablespoon measuring spoon. Then scoop out a spoonful of yogurt and use the straight edge of a knife to make the top of the scoop flat. Place the spoon just above the surface of the sodium alginate solution and slowly tilt it to pour the yogurt into the solution. If you'd like, you can use a second spoon to help scoop all the yogurt out. Stir the bath gently without touching the yogurt sphere. Wait for 2 minutes and then carefully remove the yogurt sphere from the sodium alginate bath with a spoon. Rinse it briefly in a bowl of water and then take a closer look. Hold it in your hand and squeeze it slightly. How does it feel? You want the gel layer surrounding the yogurt to be as thin as possible, but it also needs to be strong enough so it doesn't break when you hold it. While the reverse spherification process may look like magic, it's simply a chemical reaction between sodium alginate and the calcium within the food mixture. Sodium alginate is made from seaweed and consists of alginate, negatively charged molecules called polysaccharides, and positively charged sodium ions that bind to the alginate molecules. When dissolved in water, the alginate separates from the sodium ions and forms a liquid. When the calcium-rich food comes into contact with the sodium alginate solution, the alginate molecules bind to the calcium ions within the food, forming calcium alginate. As the doubly charged calcium ions can bind two different alginate molecules simultaneously, the outside of the food mixture thickens and becomes gel-like. This is why the outside of the food mixture gets firmer. It is a shell of calcium alginate. When removed from the sodium alginate solution, the reaction stops as the calcium is no longer in contact with the sodium alginate. In reverse spherification, the chemical reaction that forms the yogurt spheres can be written as the chemical formula: two molecules of sodium alginate react with one calcium ion from the calcium salt to form two sodium ions and one molecule of calcium alginate. Since both reverse spherification and direct spherification use the same chemical reaction, let's take a moment to compare the two techniques. In reverse spherification, the calcium-rich food is dipped in a setting bath of sodium alginate. In direct spherification, it is the opposite. The food is combined with sodium alginate and dipped in a setting bath with calcium. Use reverse spherification when starting with a food that contains a lot of calcium, or when you want to more precisely control the stopping point of the membrane that forms around the food. In reverse spherification, the gel membrane builds from the surface of the food out, is tasteless, and stops growing when you remove it from the setting bath. In contrast, in direct spherification, the membrane grows from the surface of the food inward, is flavored like the food, and continues to grow slowly even when removed from the setting bath. Although the chemistry and technique of the reverse spherification process are fairly simple, getting the conditions just right can be challenging. There are several variables that affect the process. As mentioned before, the calcium content of your food is important. Without enough calcium, the reaction with the sodium alginate will not happen. If your food does not contain enough calcium, you will need to add enough calcium salt to make a food solution with about 0.2% calcium. The second variable that can affect spherification is acidity. If the pH of a food or liquid is not right, the sodium alginate does not solidify. The spherification reaction will only occur in a pH range between 4 and 10. Sometimes it can help to add a couple of grams of sodium citrate to the food mixture in order to increase its pH. It can be helpful to check the pH of your food mixture with pH test strips before you start the reverse spherification process. Another variable is the viscosity of your food. The ideal consistency is that of thick cream. If the liquid is too thin, it will not be submerged in the sodium alginate solution. If you see your food spread in the bath and fail to hold its shape, you can add xanthan gum to thicken the food. Usually, a final concentration of xanthan gum between 0.2 to 0.5% within the food solution should be enough. Also important is the amount of time the yogurt spheres spend in the sodium alginate solution. The longer you keep them in the solution, the thicker their outer gel layer will be, as the alginate has more time to react with the calcium within the food. Since the reverse spherification process is dependent on many variables, you can easily turn the making of yogurt spheres into a science project. Time in the sodium alginate solution or food acidity make great independent variables for a science experiment. For example, you could investigate how the thickness of the outer gel layer changes depending on how long you keep your yogurt spheres in the sodium alginate solution. To do that, you could measure the weight of your yogurt spheres at different time points after you place them in the sodium alginate solution. How thick can you make the outer gel layer of the yogurt spheres, and what is the perfect thickness? Experimenting with reverse spherification is the best way to find out. To get ideas for reverse spherification science projects or thousands of other science and engineering projects, visit us online at www.sciencebuddies.org.